Okay. So yeah, thank you all for coming tonight. I'm going to be doing this lecture on natural language processing. My name is Joshua Tom. I'm a sophomore, computer systems engineering, and what we're covering today is a really you can see it both ways. It could be really interesting or it can be really boring. And I'm going to try to present it in a way where it's more interesting. So there's not going to be a crap ton of math or like confusing things, hopefully. If you do see something that is unfamiliar, just stop me and let me know. So yeah, natural language processing. We're basically going to let computers understand words, language, anything where we're speaking or interacting with words. Obviously, computers don't speak English. Um, they don't speak any language other than numbers and signals. So there's a lot more information that we have to provide in order to properly give a computer the word apple, and it takes something away from that that's more than just an on and off signal. So the way that we're going to do that is we're going to translate it through a few different methods so that in the end, a computer is able to understand what's happening. So natural language processing it happens pretty much everywhere on the internet, on computers, anything that is interacting with text, so text classification, chatbots, so like ChatGPT, information extraction from documents, translation, so from one language to the other, and summarization, so pulling from a bunch of texts, question answering, sentiment analysis. Yeah, so sentiment analysis is where it's like it'll see a text and then it'll say like, is that positive? Is it negative? Is it racist? Is it not racist? Blah, blah, blah. So that's natural language processing. And I said it's used in chatbots and that it literally means everything with AI. So ChatGPT, all the LLMs out there, every single like AI like hype thing, natural language processing is in that to some degree for all of them. So just allowing the computer to understand words is one thing, but applying the computer's knowledge is something entirely different, but also the most interesting part. So we'll be covering three main things throughout this. So the first thing is translating. So representing a word for a computer so it's understandable. And then the second thing is using these words with neural networks so that we're able to get something out of it, not just putting the word apple into something a computer can understand. What can we do with it? And then the last thing is, it sounds complex. It's just going to be an overview of things, but I'm going to show you how natural language processing ties into large language models. So the entire thing of like taking in an input and then thinking and reasoning or like all that information. And I'm going to try to go through every step without doing too much. But yeah, by the end of this, you should kind of understand how we can communicate words and language to a computer. So yeah, um, there is there are ways to talk to computers that don't require neurons, that don't require training a crap ton, and they're also very old. So we have one called Eliza or something, 1966. Yeah, yeah. And it's a chat bot where every single response is hard coded into it. It's a crap ton of if-else statements, and it's supposed to be a therapist. That's not what we're doing. And then this other thing called Georgetown IBM. It's a translator, goes from Russian to English. This just uses rules and if-else statements, that kind of thing. So what we're trying to do is not use that, because obviously we can make something like this in like 20 minutes and we're talking to a computer, but no, this is just rules. And then, yeah, so we're trying to go beyond this. Okay, so translating the words for a computer. I don't think this is mainstream, but I kind of broke it down into two different parts. So we have a preparation phase And this is consists of two things. So it's tokenization and normalization. And tokenization is literally just how we structure things, how we structure a sentence. And normalization is just kind of like clearing things up. I'm going to explain all of these subjects in the next few slides. And then the second phase is the definition, where we are actually putting meaning into these representations, into these tokens or little like bits of data. So how are we actually providing meaning to these numbers? And there's two ways that we can kind of go about it. One, where we just look at the entire text and how numbers appear and how words appear. And then the second is actually assigning value to words based on like appearances or just some other method. There's basically, there's a few different ways that we're going to be using vectors, and I'll explain all of this. So, all right. Oh, we're starting the first part of what is tokenization. It's so boring, but it's literally just breaking down a sentence into chunks. Tokens, it can be whatever you want. So let's say we have a sentence, drinking 3 liters of Sprite in an hour can be fatal. We can break that down into word tokens, so like how we kind of think about sentences. So each word is its own part. That's it. You can do subword, and this is kind of what more modern models use, and that's breaking things down into syllables or components so that in the future you can actually combine these in the situation where it's an unknown word. That's what subword tokenization is. You can be weird and do all of the individual characters as a token, or you can just have the whole sentence as a token. All this is what is the model going to look at as the chunk of data and then put meaning into that chunk of data. That's all this tokenization is right now. And then removing stop words, that's like the cleaning up, normalizing thing. Unless there's a different thing, it's just word tokenization, but removing the extra stuff. So in the sentence, 3 liters of Sprite can be fatal, remove the of, remove the and, remove the can, whatever. So just like make things more concise. There's more ways to do it, but that's basically what's happening, where we're clearing things up for models that either can't handle that amount of data or just like to keep things smaller, because models get pretty large. And actually, interestingly, after tokenization, we can kind of generate words from there. And they're called n-gram and Markov chains. And these are statistical, sequential and probabilistic models. Basically, all that means is based on what's around this specific word, holy moly, sorry, based on how many of the words are in a text or what's next to it, that's all that's being saved. That's how all of the words are generated from there. So for a Markov chain, on the theory side, it's the future is only determined by the present. So it's like if it's raining, you're not going, or if there's a storm coming, you're not going to look at like yesterday's weather. You're going to look at now's weather and then predict from there. So that's kind of what Markov chains are doing. So in this case, so let's say we have these 3 sentences. So we have the cat walks, the cat jumps, the cat meows. Just if we have the word cat and we're like, what is the next word going to be? Just looking at what comes directly after cat in the data, we have walks, jumps, and meows. So in a Markov chain, that's a 1 in 3 to generate either the word walks, jumps, or meows. That's all a Markov chain is. And then n-gram just gives it more context, I think, kind of. Basically, you can go back more. Instead of just looking at the word cat, you can look at the cat or the fat cat or whatever. And then from there, you can reference, hey, does the cat appear in the text, and what typically comes after that? Does the fat cat appear in the text? What typically comes after that? So it's just basing it off more and more context. But there are a couple of issues that can arise from this. Since it's just statistics based and numbers, it's not going to be as it's not going to be anywhere near as good as what we actually think a model should perform as, like, it's not as good as we want. Context. There is basically no context for Markov chains. If we have the man ate the Markov chain is only looking at the. Like everything it's generating is just based off the word the. It doesn't factor in ate, it doesn't factor in man, so no context there. And then for n-gram, you can kind of go back, look through the text and say, hey, how many times does ate the appear? Or how many times does man ate the? But if that doesn't appear in the text enough, we don't get enough context. So as we get more and more like diverse outputs or like inputs and like different words, things can kind of fall apart for these two models because they just don't have enough information to realistically generate what we want. So yeah, that's just kind of like the intermediate step before we actually get into neurons, which is, this is just based off of sheer numbers, no calculations, just what's the probability of the next word based on what we've seen before. So let's try, instead of just looking at what comes before and after, let's just try using vectors. And what I mean by that is just a long list of numbers to represent a text, an idea, or a word. And we can actually use vectors to represent the entire text. This is pretty easy to understand. This is one of the more easier representations and uses of vectors in this natural language processing idea, where we have something called bag of words, where we take a sentence. So what if we represented the entire text using word counts, and then we get the vector here, 1, 1, 1, 1, 2, because the word the appears twice in this thing. So that's bag of words, is it represents the text based on what the word is and how many times it appears. It's obviously there are some shortcomings to representing your entire text with how many times a word appears. But then there's, okay, this is weird. TF, IDF, term frequency, inverse document frequency. You don't really have to care about what those mean. Basically, it's the more rare the word is, the more importance is assigned to it. So since the word the and appear a ton in a book, but the word murderer might only appear once, maybe the word murderer is going to be weighed way more highly than the words the, and, or So that's kind of these easy vector ways to represent a text. It's not supposed to provide like a summary of what the text is. It's not actually supposed to provide a lot. All it is a fingerprint, a quick summary of what the text is in a way where you can kind of get the idea of what the text is. So like here, if we look at this text, it's got doctor, patient, hospital, nurse, scalpel, a lot of medical stuff. It's also got tackling, contagious, untreatable, panic. So if we were to use bag of words, well, the bag of words looks at that list and it says, hey, patient shows up a lot, doctor shows up a lot. That means that this is probably a medical text, just based on how many times the word doctor and scalpel and all these medical things show up. And if we were to use TF-IDF, it might look at the more unique words. So panic, tackle. Hey, maybe there's more information to this text than just being a medical document. So that's kind of how bag of words and the TF-IDF differentiate. These are very basic representations of a text, and there's only so much information you can get from it. But this is without doing any weird multiplication matrix thingies. And we're gonna move on from just this shallow representation to actually getting real meaning into a word. Now, words as vectors is not necessarily the easiest idea to just intuitively grasp. So I'm going to provide a figurative example. It's a toy example. This is not how vectors are actually encoding meaning into a word, but let's pretend we have 3 traits. So we have the trait red. Is it red or not? Fruit, is it a fruit or not? And is it spherical or not? That can be either on or off. So if it's on, it's red. If it's off, it's not red. if we have something that's red, is a fruit, and is spherical, ones for all of those, that's an apple. We can pretend that's an apple. So that means the vector representation for apple in this case would just be 1, 1, and 1. But if we were to turn red off, then we'd get an orange. So 0, 1, 1. And then if we turn off fruit and off sphere and keep red on, we get, like, I don't know, some fire hydrant or something. Basically, these are representations of words or ideas using numbers. So while it might not make a ton of sense to think, like, how am I going to put the word computer into a series of words, this is kind of a way to think about it. Features turned on and off, or how on or how off is it turned, like, so you can kind of think about it like, what are the traits and how strong are the traits? And that's what the numbers represent. Of course, it's not that simple. And words aren't made up of just 3 traits. And thankfully, large language models actually use vectors. Instead of just using 3 values, it can use 3,000, or some can even use 13,000. But wait, if there's 13,000 numbers in a vector that's supposed to describe a word, but there's so many more words out there that are either adjectives or descriptions, how is a model able to have, like, every idea, like, tied in there? Or, like, there's a level of abstraction that you kind of need to understand for this subject, for, like, this specific topic of deep learning, where not everything is concrete on and off. Not everything is like, this one value does not necessarily represent being read or not. The way that these are calculated is multiplication after multiplication, millions and millions and millions of times. Values are changing each other. So by the end of it, the model understands what each value means. We might not. If you switch the value for one vector and crank it from like 0.2 to like 0.8, it might, like, change what the model thinks that word is, from just like a building to like a brick. Like, do I know why that one specific, like, what that one specific vector means? No, but as long as the model does, and as long as it's able to generate words properly, that's all we care about. So yes, in this lecture, just keep an eye out for when I'm, like, abstracting things and giving, like, concrete things. Like, you can think, oh yeah, that's how these vectors work, but that's, like, if you were to look at the code of things, that's not what you're going to see. So yeah, that's just kind of the FYI. So yeah, let's provide more information to a word now, instead of just 3 traits. So there is this technology, this discovery from 2013 called Word2Vec. And the way this works is we give meaning to words based on what's next to it. So in this case, we have a bunch of different sentences. So the cat runs through the field, the tiger swishes its tail as it runs, lion runs, blah, blah, blah. So you can see that for every word, like, you can see that cat and runs appear together, tiger runs appear together, lion runs. All of these, like, are shared. That means that maybe based on context, a cat, tiger, and lion might be similar things, but a lion might be more different than, because it doesn't have that tail vector. So there's relations that we can create just by having words next to one another. So that's kind of what Word2Vec does. Okay, it says it's going to get technical. You're going to see some, whatever, just like, yeah. Okay, yeah, it's not that bad. So let's say we wanted to create the contextual embedding for the word cat. Just start with a sentence. So a cat swings its tail. We're going to ingrain the idea of a tail and the word swings with the word cat. So we can just start with random vectors, where, again, toy example. So obviously, there's not 3 values representing these 5 different words, but you can think of it like something like that. When we I actually hate these slides. Okay, so you can actually look at what is our goal here. What we're going to do is provide the word cat. We're going to see that, hey, when we take this vector cat and we check it against all the other words that's possible in this sentence. So we take the cat vector and check it against A, swings its tail. We check it against those and we see, hey, what word is most likely to come after that? That's the process that we're going through. And we want to move how do I put this? Take the word cat, output tail. We want those two vectors to be more closely related to one another. Oh man, there's a leaf in logic. Okay, wait. Does anybody have questions? I've gone way too far before stopping for questions. Yeah.
So it depends on what the word means in a sentence. For example, uh, a mitochondria is the powerhouse of the cell, and the prisoner is in the cell. This word cell has two different sentences. This cannot handle that.
Yeah. So I'm actually going to cover why that fails and how we can actually remedy that. But this is where things start. Like this is the biggest, not biggest, but like this is a huge way of thinking where we're putting words into numbers like that. This is the kind of foundation of like why these language models kind of exploded. This might get confusing. Okay. All right, so we can think of every word as having two different parts. The first part says, hey, how do I relate to you? And in the vector space, it's surrounded by what it predicts. So what is it going to respond, like generate? So if we have the word cat, it could be like cat tail, like cat paws, cat meows, like all these like word spaces are all right next to each other. And the other vector representing the word basically answers that question when other words, when other vectors ask that. So what predicts it? Basically, the first vector that the word has says, shows what do I point to? And the second one shows like what points to it. Because a cat has a tail, but not all tails belong to cats. That's kind of, there are two directions that these associations have. So that's kind of why we have two different representations. So just, they are different is what I want to clarify here. So yeah, you can see like, what does cat relate to? So cat has a tail, whiskers, fur, and paw. And what points to cat? So it could be like what words precede the word cat. So a cute cat, a tired cat, a fluffy cat. So there's the input and output. That's the two different vectors that make up a word. And those two vectors, being able to differentiate what comes in and what goes out, is critical to being able to actually provide meaning to a word given another one. So mathematically speaking, we take the word cat, we run it through the input matrix, cat, and then we run it through the output matrix and we get a word distribution. So we checked the word cat against all the other outputs and we got the response of, yeah, 0.26% chance of generating tail. What is actually happening here in an easy to understand way? We just took the cat vector, multiplied it by the tail vector, and the output from that is how likely cat is going to be followed by tail. That is all that is happening throughout all of these matrices. It's just like, how likely is tail going to end up after cat? And interestingly, if we want to make cat remember tail a little more, like bring the association closer, all we have to do is nudge them together. So let's make cat and tail more similar. So next time that cat is put down, there's a higher chance that tail is generated. So it could be something like multiply cat by 0.02 or like add like or subtract 0.12 to all the values of tail. as long as that nudges the two vectors together, so now there's a higher likelihood, that actually that is the basis for everything, nudging the values together. So imagine this. We have a huge, huge text. The word cat appears with tail 100 times. Same with per, eye, fur, and paw. Every single time we take those word pairs, we nudge cat a little closer to tail. We nudge cat a little closer to paw. And over time, we're able to get a vector for cat that has been nudged by paw, nudged by tail, nudged by whisker 100,000 times, so that it is basically, at that point, that is how it relates to all of those features. That's a leap in abstraction, but you can kind of think about this as well. If we have the word dog and we say, hey, dog got nudged by tail like 200 times and so did cat. So that means in relation to tail, cat and dog should have some sort of similarity, some sort of relationship between the two of them. So if dog and cat appeared the exact same amount of times for tail, paw, eyes, and fur, then they're going to be pretty darn similar in relation, in how they relate to those specific vectors. So they might both be on like the far left quadrant, like over here. But as you can see, cat purrs, dogs bark. So there's a difference there. So they might be similar in terms of like their physical features, but then like barking and meowing, so they're slightly different. These relations to one another. So how does dog relate to tail? How does cat relate to tail? That is how we're building meaning. So even if these numbers might have started meaningless, as we used all of the text and we related tail back to dog or tail back to cat or tail back to the word like a, like we're able to figure out how closely are these words related to one another? How closely are these words relationships similar to another word's relationships, and create a lot more meaning. This is a representation of all the words in Word2Vec. It's a crap ton of values, and basically the coolest thing that I think you can get from Word2Vec, aside from being able to create vectors that represent specific words, is you can take the direction between words. So we have a easy to understand example, boy, girl. If you take the difference, like the different vector between the two of them, you now have a vector that you can assume represents something along the lines of going from female to male, male, female, like gender. In the example of the dog, in the example of barking and meowing, you can say that the difference between where dog and cat is represents like what they say or like what they output. So you can take this direction, this female to male direction, and actually apply that to other words. So we have this female to male direction. If we apply it to the word queen, you actually end up with the equivalent in this specific case. So from queen to king. So you're able to take these differences and just kind of apply them generally. So these directions are the features that kind of relate things to one another. So girl is related to boy by the gender like strength or like gender vector of like 1.2 or whatever. So that's how that could be, so that 1.2 male female vector could be the first value in that vector, in the vector representing boy. And then in girl, that could be 0. So that's kind of how each of these values in these words and these relationships, as there's more and more and more values in a word, you can get more and more relationships and more meaning. So that's kind of how we can create words that start to have a semblance of coherence and meaning. And if we want to take, like, yeah, there's a small issue with that. So if we look at the word bank in Word2Vec, there's only one. And it's going to encode the meaning of riverbank, so how like water flowing, and money. But Also, it doesn't like explicitly lean one way or the other. It might be like directly in the middle, or it might not even be anywhere close to those. And that's because there's no context that's assigned to these vectors. And the solution to that is a little too, yeah, we're not covering that right now. There's a lot of math and matrix multiplication, keys and queries, and we're not covering that now, but you should keep in mind the flaw that we have with word2vec, where there is only one definition per word, and we need to get more meaning into that somehow. But that's a problem for later. Right now, we have words that have semantic meaning, so that's huge, and we're going to go to the next part now. So we've defined the words. So what's next? We can go words, language, ChatGPT. No, we are not going that far because that's also really complex. All we have right now is a pretty solid vocab, albeit weak in terms of multiple definitions. So I did say that we're going to work our way to getting to a large language model, but we have to start small. And the smallest you can get is a neural network multi-layer perceptron. Basically, we are going to create something where we can take a word, put it in, and then without hard coding things, it's going to output a word. That is what a multi-layer perceptron is. And it's super basic, it's super old, it is the foundation of quite literally everything because it uses neurons, it's a neural network. So yeah, we're gonna start with what a multi-layer perceptron is, and then we're going to move in a more language-focused aspect. You can move more towards vision, that's convolutional neural networks, that's a bunch of different other architectures, but we're going to move towards words. So a recurrent neural network is just memory. So like we remembered before, if there's only the word the, it would ignore like the context before. So the man ate the, or the girl jumped over the. So there's a lot of context that we're missing. So a recurrent neural network isn't perfect by any means, but it is the first step to adding memory. From there, we go to an LSTM, which stands for long short-term memory. It's pickier memory, allows for greater detail preservation, and then we're going to go to attention and then transformers. I'll explain how those kind of tie into each other, but it was too many words to fit in that one spot, so I just didn't. Oh yeah, questions? Is anybody confused about anything yet? Oh, sweet. Okay, so what is a multi-layer perceptron? Okay, I already ranted about this. It's the super foundational thing. But what we want is we can use neurons. This is what it looks like. Okay, yeah. So this is the multi-layer perceptron. We take the word bird, run it through the input matrix, run it through something called ReLU, run it through an output matrix, and then we get a word distribution. It's a lot, but everything gets like, it's not as bad as it looks. So even though I said we weren't doing math, I'm just gonna kind of show some of the technical parts because it's not as bad as you guys think, hopefully. So we start with the vector representation of the word bird. So that's kind of like the orange, whatever. I'm hoping you all are following vector representations of words. And we run it through a layer. Now this layer is made up of neurons. So this is one neuron and it consists of a bunch of values. And what these values are, what these neurons are, this is kind of similar to like the 3-value thing. Like this isn't exactly what's happening. This isn't exactly what's being searched for, but this is a good way to think about layer one, is each neuron is checking for a feature. So we have feature neuron detector 1. Is that word a noun? And what it does is it has requirements. It has values. And if those values line up with what bird represents, it'll output more highly. So if bird matches everything that neuron 1 wants, it's going to output that this is a noun pretty strongly. So 70% or 0.7. And then if we look at the next feature, we can do, is this word an animal? And all of these neurons are checking for different features. Is it an animal? Can it fly? Is it an adjective? Is it a verb? And that's kind of being, they have like a template. You take the bird, you check it against the template. How similar is it? And then output the similarity. That's what's happening here. And what happens is, by the end of this, by the end, after we've checked bird against every single neuron, we kind of get an output of what does bird mean? Like how do we represent bird? So it's 70% a noun, it's 90% an animal, it 100% can fly, it like 10% has, I don't know, like hair or something. Basically, there's a lot of, this is, oh yeah, I'm also gonna represent this summary vector, feature vector with this like pentagon. Anyways, so yeah, that's kind of what the first layer of an MLP is doing. We're extracting the details from the word bird and actually getting something of meaning. And then we can actually, before we run it through the second layer, so okay, I need something to hold. Okay, so if I like had this bottle and I'm trying to describe this bottle to you, if I said something stupid, like this is not a table, guys, like this is not a computer, like that's like completely useless. Saying what something is not doesn't really send us information. It's not really, I don't know, it's just annoying personally. But so what happens is we also can have negative values. So we check, hey, is this thing like a lizard? And it outputs like -1 because it's not a lizard. Like, okay, good to know, but we can also just, we don't need to know what it's not. We just need to know what it is. So what we do is something called ReLU, which means rectified linear unit. I don't actually know what that means, but all that happens on a technical level is we zero out the negatives. So that's kind of cleaning things up. That's just making things less confusing. It doesn't have the, I don't have something. There's other methods of doing it, but this is the one I'm using now, and this is the one that is used most normally for lower level MLPs. And now we go to, so we have our vector representation, we've cleaned it up a little bit, and now we're going to look for an output. So very similarly to what we did before, we take that feature vector, and imagine every single word has their template. So drop is looking for a specific type of word. Run is looking for a specific word. In this specific case, we check the features. So run might say, hey, if I'm going to output strongly, if it's got legs, if it moves fast, if it's a mammal or something, basically once we've checked bird against every single one of those word outputs, one of those word templates, we get a distribution of, okay, we don't actually get a distribution. We have to do something called softmaxing, but I didn't include that. But that's just some random math formula. In the end, what we end up with is every single word's probability of being generated, where each word, each neuron says, yeah, I think the word bird works with me the best. So I'm going to output 1. Like this fits me perfectly. That's what an MLP does for words in this case. So yeah, take the word, run it through feature clarification. That's like the description, remove some noise, choose the word, and then we get the distribution. Everything, I mean that, everything is built from this. The idea of taking an input, checking it against others, and just repeating that over and over again until we get through all of those checks, somehow like there's an output that we want. That's literally how all these neural network architectures work. And they just add like 100 more layers and, oh yeah, I'm actually going to show you guys those. Okay, so we have an MLP and it's able to predict things properly, kind of. So we're going to move to something called a recurrent neural network. And the reason for doing that is the MLP can only see a single input. So if we do a fat, wingless bird, run it through the MLP, we're going to get flies regardless of what comes before it. That's an issue that doesn't really work. So what an RNN does is it provides a way to store memory in, it stores memory. I'll elaborate on what it actually is storing, but in this specific case, we have the bird, boom, we save that to memory where, hey, we have the word bird, so then we should output a verb next. That's kind of what an RNN is doing, like that's the thought process. On a more technical side, we take the MLP that we already have, the first check against like extracting the features, and then we just add memory to it. So memory is, it's not too intricate. Basically, what happens is we run the bird checking matrix against a memory analysis layer. And what happens there is based on the word the, this memory analysis goes, hey, that's an article. That's an article adjective. I'm going to mark that there's an article adjective, so next should be a noun. That's all it's really encoding. And then it kind of adds that to the bird vector. That gets saved into the memory, and then it just goes on about its normal thing. And there's kind of the result from this is we get the bird 8. Okay, so 8 gets saved. Saving something into memory would be like, hey, there's the word eating. That means the next word should be something food related. So it could be the seed. And that's kind of what memory allows. Without it, it could be like chair or table or I don't know, elephant or something, just something completely unrelated. All this memory is doing is providing very small bits of context like this is food or this is an adjective or hey, this is a noun. That's typically followed by a verb. That's all this memory is really saving on a low level. Now, this can result in a few issues since it's super grammatically weak. If we have a sentence that's like 10 words or 20 words with multiple nouns and multiple verbs, that could lead to, for example, like the bird flew across the yard and ate the, well, shoot, it forgot, it doesn't know that it's supposed to be a bird. It doesn't know where it's flying. It just knows ate the, so it'll give a food. It could be like an apple, or if it was contextually relevant, it would be like a worm or something. But that's kind of why if an RNN is saving, hey, we just flew across the yard. Yard is the subject. Okay, well, you forgot about bird. So that's kind of, we got to fix that. And the way we fix that is the LSTM, the long short-term memory. It's not too bad. So basically, when we're working, oh, right, sorry about that. Okay, so working with RNN memory, the bird flew, okay, it's focused on bird. Fast, it's kind of forgetting the specific word bird. Now it just knows an object is flying, and then it only looks at the word wall, and then from there just degrades. So that's kind of how things can be overwhelmed. With an LSTM, everything stays grounded, and that's super important. Subject is bird. A bird is flying a specific distance, like the yard, and then the bird makes, it's flying, so now we can do another verb or whatever. So as the LSTM allows us to focus on one subject and stay on the subject, whereas an RNN just, it doesn't focus on it. So yeah, it uses something called gates where it can choose what to forget and what to remember. This is a little more complex, so I'm not going to go too far into it, but basically we start with our old RNN, and then we basically say, hey, oh yeah, so instead of constantly modifying a memory and then shipping it back in and then pulling it out and then shipping it back in, we just kind of have one memory kind of just floating out there. It's for the most part, unchanged. It's slightly modified, slightly tweaked. And we use a forget gate, an input gate. Forgetting is like, what should I remove based on the memory? And what should I put in based on the memory? So if it's like, we flew across the yard and it's like, okay, we finished flying across the yard, we can forget, oh, okay, sorry. We flew across the yard and landed. Okay, we can forget that we flew across. We can forget about the word flying. That's kind of what the forget gate is for. And the input gate is, it could say landed. So, okay, now we add the context that we are grounded. We're still in the yard though. We haven't forgotten that we're in the yard. So that's kind of what that does. Remove useless stuff, only add this. And then an output gate kind of says, okay, the output gate kind of says, hey, you don't need to take the entire freaking memory and apply it to the model thought process every single time. So just provide what's relevant. So, hey, this was a bird. If that's all that matters, that's all that we should send. That's all the output gate does. Wow, we've added that. So all of these components kind of keep a safe area to store information. And that's why LSTMs are more useful. And oh man, wow, I just go straight there. Okay, so yeah, the math behind it gets a little more complex, so we're not going into that. So we have this kind of floating memory, but again, there's only so much that this kind of memory system can do. The words are stuck to a specific definition. The context can only get so large. Like, you're telling me the cell state has to store like an entire book? I don't think so. Is it able to say how things relate to one another? At a certain context point, things start to fail. That is fundamentally why we're moving from an MLP to an RNN to an LSTM. It's just as we go bigger and we want more detail, more context, things just start to fail. So what if we just kind of, instead of forcing cheap summaries where it's like, hey, this is kind of what happened, like in the smallest possible form or most efficient form, this is kind of what happened to these specific words. What if we kind of just got rid of that floating memory, floating summarized condensed memory, and just kind of let it look at everything? This is what attention is. It's a crap ton of queries, keys, and values. It's used in modern LLMs. Basically what happens, we'd run it through the normal LSTM, it outputs a memory. As you can see, there's multiple other memories there, M1, M2, and the new M3. And then when we generate the next LSTM, we can have it ask, hey, I just received the word the. What's the most relevant information that I should take from all of the previous memories? So checking M1, M2, M3, figuring things out at its own pace instead of everything getting like condensed and then regurgitated over and over again. Now it can just look for it and figure out what it wants with its own amount of detail. So it could say like, hey, that's related to food. It's a person named Steve. It's like, okay, now I can contextually generate a specific answer like apple. And that's, oh man, that's such a weird representation of attention, but that is what's happening, is we are allowing words, we're allowing a model to kind of pay attention to what's happened before. So as it saves things over and over again, we get a longer, just saved context. Obviously, this isn't as small as having that condensed memory that spans the entire length, but it's not bad. Like it's not using a crap ton of information, and it's allowing genuine like understanding of sequences of events. And from there, we have that issue where, word can only mean one thing at a time. So we can use this tech called self-attention, where instead of having us look at memories, we can just look at the words themselves. Like, why do we have to look at like what's happened before? We can just look at what we have now. So in this case, this is something called multi-head self-attention. Let's say we have one head of attention. This is the subject head. We have the sentence, a fat bird eats a red worm. We can use the way that self-attention works in this case is it has all of the words relating to one another. They're able to look and see how they are relevant to one another. So in this case, we can have like, hey, A references the word bird. Oh yeah, and then the worm is affected by the bird. So that's kind of how nouns relate to one another. But it's called multi-head self-attention. So we can have another head. So this one's the description one. So it could be like the adjectives of a fat bird, or a red worm. And what these are doing, they're not just pointing at each other and saying like, hey, I relate to you. It's encoding the fact that, hey, I'm next to like, it's like, hey, I'm next to the color red, or I am described by the color red. All of that information is added into the word bird. So by the end of it, we have every single word vector in that sentence. A fat bird eats a red worm. All of them understand where they are, how they relate to one another. So bird understands that it's fat, and it understands it's eating a worm. The worm understands that it's red, and that it's going to get eaten. That's solves the context issue. So if we have riverbank versus money bank, using this self-attention, we can be like, hey, there's river before me. So that changes my meaning of bank. So that narrows things down. That is the point of having self-attention here. Is it allows for more meaning to be ingrained based on what all of the other words have. And multiple heads does not just have to stop at noun and adjective. It could be what tense am I? What language am I? How far along in the sentence am I? What punctuation am I near? And everything just gets tied together. There's a more technical way to present this, but this works. This works for explaining how words can be affected by other words and how they're able to kind of enhance their own context. So, where are we now? We've made a lot of progress, and I'm sorry that I've kind of rushed through a lot of content. Basically, we went from just using a just the distribution of words in the entire text, so the entirety like Moby Dick or something, and just seeing like what word comes after the other. We went from using that to predict words to using neurons, like matrix multiplication, keys and queries, and words tying into one another. And that turns word generation from a statistics game into kind of something that actually resembles how we think and speak and communicate. So we've managed to translate our language to a computer, and from there the computer is kind of able to spit back language that we can understand as well. All of those different layers tying together. Unfortunately, we're not close to what an LLM actually is. That is a lot more layers, but it is all fundamentally built on what we've already explored: multi-layer perceptrons, self-attention, multi-head self-attention, the concept of words relating to one another just over massive contexts, getting way more detail. If we were to put our little self-attention module and put an entire book in there, there's no way that would actually get all of the meaning. So we'd have to use a more robust, more, I guess, like adequate system and architecture. So it's not, we're not perfectly there, but we're getting there. There's, it's a lot of work to get to an LLM from here, but that doesn't mean that we haven't done anything. We've prepped the text, so that was tokenization. This is just kind of going to be a summary right before the end. We've prepped the actual text to be processed for a computer. That's tokenization. breaking things down from a sentence into words. We've added meaning to the words via vectors, albeit shallow meaning through very basic, just checking like, hey, how often do things occur with one another? Then we're able to use neural networks to generate words. So probabilities. So we take this vector, run it through. We added memory, some weak form of memory. We've added more precise, gated memory that is able to keep things more consistent. And then we broke down aspects of LLM, so it's attention, self-attention. And fundamentally, we now have a program that's able to understand our language and is able to generate relevant information. And that's what natural language processing is. There's more to it, kind of, but as long as you're able to understand that we've translated what we say, what we write, maybe even our actions and just like everything like that into something a computer can understand, and then we can understand what it says, that's really it. But as you can see, like we could scale that up massively to create the large language models, the attention and all that kind of stuff. So yeah, do you guys have any questions about this? Like, like after this like slide, or like, no, next session? Oh, in general, okay, yeah, you're right. Yeah, transformers come right after this. That's just kind of a lot of self-attention, just kind of stacked on top of one another, and 50 other things. But yeah, that's what's next. Anything else? Yeah. What did you say? Yeah, they'll be uploaded. Alrighty, cool. Well, that's really it for this. So yeah, thank you guys all for coming. I appreciate it. There is there is a lot of information that can be explored into, like Markov chains and like where they actually like came from, and like the actual like more robust applications of them and how to like grow them, and like a lot of different aspects of it. But I think I've covered most of what natural language processing is, and I hope it was in a way that was somewhat understandable. So yeah. Yeah, thank you. Uh, oh man, there's so much. Oh yeah, so just saying, next session is going into large language models. So actually making that leap from, hey, these are little natural language things, to, oh yeah, this is how ChatGPT works. So I'm going to be covering that too, how all the different steps kind of work, hopefully in a way that's understandable. But yeah, that's next week. So yeah, just keep an eye out for that. Forget anything? I don't want to do GPT-2, GPT architecture. You should do that. You should present that. Please, please.
Hard to teach this without them. Like hidden states, encoders, decoders. We didn't.
Like, yeah, hey, thanks for coming.
Hold on, break.
There's pizza and food. Oh, wait, right. You're allergic. Was it good?
It was good. I was late. It's okay.
I don't know. How late did you get here?
I think it was like 7 minutes.
That's okay. She was here
I just
20 minutes early.
Yeah. Yeah.
My hat. Yeah, no, we got
What have I missed out?
just tokenization, nothing else. I don't actually remember when you came in. Tokenization is just literally, it's literally just breaking down words. Did you actually understand anything? That's good enough.
Vectors.
Good enough.
Yes, that's
With vectors all the same.
Oh yeah, I'm so hungry and I'm so tired.
So
We should go.
I will.
Really good session.
Okay, thank you.
When's the next?
It's probably next week. I'm gonna be honest. I spent. Oh wait, I gotta stop recording so I don't like release this. Okay. Yeah,